Okay, nice. It's time to start. Good morning, afternoon, evening, everyone. Welcome. I'm Anyok Chang from Yonsei University, and I'll be moderating today's sessions. Today's session is being recorded. Please keep your microphone muted while the speaker is presenting. Hold the questions until the Q&A at the end. But feel free to type in the chat. I'll read those questions aloud. And let's start introducing speaker. It is my pleasure to introduce the speaker today. Dr. Ritajit Majumdar is a research scientist at IBM Quantum. He is a part of quantum algorithms and engineering team, where he collaborates with researchers to advance utility-scale applications using IBM quantum technologies. He demonstrated the first potential quantum advantage candidate. He holds a PhD from the Indian Statistical Institute, during which he spent a period as a visiting scholar at IBM TJ Watson Research Center in New York with the prestigious Fulbright Nehru Doctoral Research Fellowship. And he is a recipient of the gold medal from the University of Kolkata for his master's degree and was awarded the esteemed DST Inspire Fellowship. In addition to his work at IBM, he has contributed to academia as a faculty member under the University of Kolkata and the West Bengal University of Technology. Please join me in welcome Dr. Ritajit Majumdar.
Hey, thanks a lot. Thanks a lot for having me. Just a minor correction because this will go live. The potential quantum advantage thing, that's the first from India, not necessarily from the world that I was part of. But anyway, thanks a lot for the introduction and thanks a lot for having me here. I'm really happy to be part of this, and it's really a great seminar series that you guys are organizing. So let me quickly share my screen and get started. I hope my screen is visible.
Yes, it's perfect.
Okay, great. So the work that I am going to, in fact, it's two works that I am going to talk about today. This was part of last year's summer internship. So one student who was an intern with me last summer did one of these works, and she also continued working with me as part of her master thesis. That led to two more papers, but one of them is related to the internship work that she did. So what I'll do here is I'll cover these two works, which are very similar in flavor and works on something that's called circuit cutting. I'll come to what circuit cutting is, what these are doing and all. But the primary goal, as you see from the title of this talk, is making quantum computing practical. And as I will show very quickly, is circuit cutting has a lot of potential, but it is also a bit complicated given the overhead that it brings. It brings an exponential overhead, which makes circuit cutting infeasible for most circuits that we encounter. The two methods that we will talk about, we don't claim that it is making circuit cutting like applicable to any circuit, but it is at least taking circuit cutting beyond what can be done today. And it goes a lot to reduce the overhead of this method. So let's get started with this. And let's first start with, if I have a classical circuit, a digital circuit, what do we mean by cutting a circuit? So let's say this is some digital logic circuit. We don't really need to care about what this is doing and what this is useful for. This is just some logic circuit that requires like 4 bits. Now, let's suppose that I have given you a classical computer which has only 2 bits. Can you still do this computation? The answer is yes, you can. So what will you do? You will first take say this part of the circuit. So A and B, 2-bit inputs, you get output AB. This is a single bit, so we'll store the output somewhere. And then we will do this BC and we will calculate this B bar C. We will again store the 1-bit output somewhere. And now I will just initialize this particular. So this is supposed to be an OR gate. Somehow I couldn't get the actual notation of this. So Just bear with me. This is supposed to be an OR gate. And so let's say now I'll just take the two outputs from here, put them as the inputs, and I can just do the OR operation. So what it means is I need to do a 4-bit computation, but I only have a 2-bit device. So I can still do that 4-bit computation classically. What ends up happening is I need some extra memory. And instead of running a single circuit, I now need to run 3 circuits, 3 smaller circuits, but 3 circuits along with some memory to store these outputs. Right? So it's doable. It's very simple. Now the question is that if I just replace this with a quantum circuit, does everything remain so nice? So what we realized is we need some extra memory and we need to run the circuit more than once. The circuits will be smaller individually, but more executions. There comes a problem immediately. So let's say this is a quantum circuit which has a very similar, I chose the quantum circuit to have a very similar nature, 2-qubit gate, 2-qubit gate, 2-qubit gate, single qubit gate. So here you have 2-qubit, 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 single qubit. So now if I say that this is a quantum circuit, but you only have a quantum computer that can operate on 2 qubits, can you run this circuit? Now let's try to play the same trick. So I'll take the first 2 cases, I will do the computation, and now I have to store this. Here comes a problem. How do you store? Now, this output in general, this is those of you who are already into quantum computing, you will understand this is a Bell state. But the point is that in general, if I give you a most general circuit, this will become a density matrix. So how do you store a density matrix? That's not very simple. I mean, it's perhaps not even possible because it's a probability distribution. It's a classical probability distribution of different quantum states. So how do you really store a distribution like that? So now let's say that, okay, I was somehow able to store. Now the next thing we have to do is for this part, I have to initialize Q0 and Q1 with these two density matrices. How do I do that? How do I initialize a quantum state with a probability distribution? You cannot do that. Previously, when we were talking about, these were zeros and ones. These were either 0 or 1. These were just bits. So I can just put these as inputs. If these were also zeros or ones, or even something like alpha 0 plus beta 1, we could have said that we will actually prepare that alpha 0 and plus beta 1 as the input state. But in general, when this is a density matrix, which is a probability distribution, we don't know how to really instantiate a probability distribution. One possibility you can say is that I will start sampling from the distribution and then I will put the initial states like that. Those things can come, but how many times do you sample? There will be some errors. All these issues will come into play. First is how do you store, and next is how do you initialize. But of course, there are ways to do this on a quantum computer. That's called circuit cutting. And the first idea of circuit cutting, which came from the group of Adam Harrow, they kind of motivated circuit cutting with this, that if you have a small quantum computer and you want to run a bigger quantum circuit, how do you really do that? So there are 2 types of circuit cuttings, and I'll come to each of them, but just to give you a flavor, one is called gate cutting. For example, let's say this is my circuit. I can just cut this gate. We will see how to do that, but I can cut this gate and I will end up with 2 smaller circuits, this and this. The other thing can be that I can cut along a wire. So let's say that I cut along this part of the circuit, this part somewhere. And again, we will see how to do that. But I cut along this part and I am left with this and this. So wire cutting, in some sense, you can think that these are wires and you are kind of puncturing the wire. The sub-circuits don't lose any gate because as you see, if we cut along the wire, these 2 gates are here, these 2 gates are here. But if you cut a gate like this, you reduce the number of actual gate operations required. You see, this gate is no longer there in any of these. So these are the 2 type of cutting, and you will see each of these subcircuits are actually smaller, has fewer gates. And the motivation that I will try to drive it through is, today we have 156 qubit quantum devices, and really saying that I have two big circuits which are not fitting in this 156 qubit, that is not really the case at this moment. That can be a theoretical argument that we can have circuits spanning 200 qubits, 500 qubits, 1000 qubits. But practically speaking, we don't really face that kind of situation where people come and complain that, oh, the number of qubits is too less. So the motivation that Harrow had earlier, when we only had, say, 27 qubit devices and all, that I want to run larger circuits on smaller devices, that motivation becomes a bit weaker here. But the motivation that, yeah,
一个会议报告。
sorry.
这就是在开会。
Oh, okay. But the motivation that we can have, and that's a real motivation, that's what I'll show you later also, is these quantum circuits are noisy. So when you have these 4 gates, they will incur some noise. But now when you have a smaller circuit which has only 2 gates, this will have lesser noise. So this error mitigation is the motivation for doing quantum circuit at this moment, and that's how it should be at this point. So let's dive a bit deeper into what each of these are. Gate cutting. So what is gate cutting? Say you have a 2 qubit gate, some UAB. Now 2 qubit gates, 2 points are here. First, we know that 2 qubit gates are more noisy than single qubit gates. Point 1. Point 2, most of the quantum computers we have today, they are planar, definitely the IBM ones. So if you have a 2 qubit gate between two distant qubits, say some Q1 and some Q100, which are sitting far apart. So if you want to do a 2 qubit operation between them, you have to put in a lot of swap gates. The effective number of gates increases, therefore the computation time increases, the depth of the circuit increases, the noise of the circuit increases. So it would be awesome that if we can replace these 2 qubit gates by just single qubit operations. However, it's very easy to check that there are many 2 qubit gates, including the famous CNOT gate itself, which you cannot replace by a tensor product of 2 operations. This is something, if you are not aware of, you can just go and check that a CNOT gate cannot be written as some U1 tensor U2. However, what you can do is you can write this as a tensor product where it's a linear combination of many such tensor products. This is something that we can do. So UAB can be written down like a linear combination of FIA tensor FIB, where this acts only on A, this acts only on B. And this sum over AI is actually 1. So I'll come to what that means. The sum over AI is essentially 1. What this means is, if you come back to my classical cutting reference, it kind of says that you can now actually run the circuit instead of this potentially long range interaction. You can run 2 local interactions, but you have to run that many, many times. So take an RZZ operation. This is how you cut the RZZ gate. So you see there are 6 instances. First is do nothing. Second is Z on both qubits individually. Third is you measure the first qubit, apply S gate to the second qubit, and so on. And each of them come with a coefficient. You will see the coefficients add up to 1, irrespective of the value of theta. These two cancels out, these two cancels out. Cos square theta plus sin square theta is 1. So you will see this sum over AI is equal to 1. However, it's very obvious from here, depending on the value of theta, these coefficients can be positive or negative. So this is not a probability distribution. This is what we call as a quasi-probability distribution. So if you want to sample these with this probability, you need to take the absolute of this. You can still sample with this probability. You can run these circuits, but what you lose is you lose the sign information. So one point here that is really important, these gates often create entanglement. So if I remove this gate, and I am saying that you can remove this gate by single qubit operations, irrespective of whether it's that you need to run 6 of them, how do you account for the entanglement? Well, the answer to this is you cannot account for the entanglement. But since you lose this phase information, the entanglement is lost actually. However, if all you care about is calculating the expectation value of some observable, then this is fine. It can retain that expectation information, but it loses the actual state information. So if you are thinking that I want to take the output of this as the input of my another circuit, then you cannot do circuit cutting because the state is lost. But if you are okay with saying that from this output, I want to calculate some expectation values, then this is doable. And this is how you partition an RZZ gate. But similarly, since you can write C0 or CZ like this with RZZ, it's possible to cut C0 gate or CZ gate. These are the basis gate sets that we have in IBM devices at this moment. So if you want to cut a gate, instead of a single circuit, you need to now run 6 circuits there. The other thing is wire cutting. So let's first look into a simplified notion. I'll talk about what is the simplification in some time. So let's say I have a 3 qubit circuit where there are 2 gates, U and V. So mathematically, I can write it down like all of these 3 are starting in 0. So 0, 0, 0. And you have this U gate acting on qubits 1 and 2 and V acting on qubits 2 and 3. Now, this is an identity. I can always insert identity anywhere, right? It doesn't matter. So let's say that I have inserted an identity between U and V. So I can write down identity like this. This is the decomposition of basis. So we know that whenever we have this projective measurement basis and we sum over the basis, it adds up to 1. This B can be 0, 0, 1, 1, plus, plus, minus, minus, any direction you want. So let's say now I am inserting an identity between V and U. So I can write this down like this mathematically as we discussed, and this acts on qubit 2. Now what I can do is I can say that this part is my first circuit, this part is my second circuit. What does these arrows mean? This arrow means that I am going to measure in basis B. And this arrow means I'll prepare in the eigenstate of B. So it's in some way measuring the state in a basis and preparing it in the eigenstate, corresponding eigenstate of that measurement basis. And now you can say that, okay, it seems this part depends only on qubit 1 and 2. So this part becomes a subcircuit. This part depends only on qubits 2 and 3. This part becomes another subcircuit. And I need to run this multiple times for different types of Bs. So here, if it is 0, 0 plus 1, 1, I need to run it twice. So this is how you do wire cutting, right? Now, what is the simplification here? Why did I say that this is a simplified notion? The simplification here is that the fact that I am saying you can write it down as just 0, 0 plus 1, 1. So measure only in 2 bases. Measure only in, measure in 1 basis that have only 2 parts. This kind of naturally implies that the state remains a pure state throughout the computation. If it is not a pure state, in general, this will be a density matrix rho. And if you get the information of only 0 and 1, you don't get the full information of a density matrix. So that's why I said this is simplified. It's assuming that it's a pure state throughout the computation and you get the entire information through that. In particular, if you think of a more generalized view where this can be a density matrix, then you can write down this expectation value of an observable O given a quantum channel phi. So this becomes a bit complicated, but eventually you will see that this is my density matrix. This is the measurement basis, the Pauli basis now. Now it cannot be just 0 plus 0, 0 plus 1, 1. It needs to be a Pauli measurement basis. So this is my Pauli measurement, and this is the eigenstate of that measurement basis. So when you measure in basis I identity, the eigenstates are 0, 1, x plus minus y plus I minus I, z again 0, 1. So essentially speaking, you again the same thing, just like gate cutting, you need to measure in a particular basis, you need to prepare in the corresponding eigenstate. So this is what's happening. The previous one was simpler to understand, but it made an assumption that the entire computation keeps the state pure. This doesn't make any such assumption. It can be a density matrix in general. So from here, you see that you need to actually do total of 8 circuits. But you can again say that, okay, but I and Z are same. So doing those bookkeepings that, okay, if I get 0 and 1, I can use that information for both Z and I. Measurement in Z and I basis are the same. So using these information, you can reduce the number of circuits required for that. So as I said, that we are looking into circuit cutting not anymore as a method to run bigger circuits on smaller devices, more as a method to do error mitigation. So these are two works that I have been part of, but there are way more works. So don't think that I am the only one working on this. Many people has worked on this. This is a periodic Ising model over 109 qubits. This is available in the IBM Quantum Learning platform. Here you see that since it's a periodic boundary, getting the connection between the last qubit and the first qubit, that leads to too many swap gates because it requires a long range interaction between the two extreme ends. And therefore, if you just run it by transpiling, it gives a very poor result. On the other hand, if you just cut off that periodic thing and run the circuit a few more times, just as we discussed, you need to run it multiple times, you get a much better result. And this is without having any other error mitigation. This is just the effect of circuit cutting. So you can see that circuit cutting itself can improve the result significantly from uncut one. And you can improve on top of this by putting in other error mitigation methods as well. So here is one example that we did in IEEE Quantum Week 2024. This is on VQE. So here, as you see that as you cut the circuit with resilience level 1 means T-Rex mitigation. So when you don't cut the circuit, even doing T-Rex mitigation slightly improves the result. The ideal value was -5 here. And as you cut the circuit together with error mitigation, you see it actually reaches very close to the ideal one. So there are, as I said, there are many other such examples. Now, the question then is, if this is such a great method, why don't we use it more ubiquitously for all the problems that we are looking into? The reason is, let's look into the gate cutting, and it will be obvious to you that wire cutting will have the same disadvantage. So let's say this is a U1, which I will just partition as FI and FIA and FIB. And this is U2, which I will partition as FJB and FJC. Now this one, I need to run some AI times. This one, I need to run AJ times. So if I cut both of these gates, I need to run the circuit AI times AJ this many times. So it increases exponentially the number of circuits that we need to compute. That increases exponentially with the number of cuts. This tells us why we cannot take any arbitrary circuit and keep cutting the circuit and making it smaller and smaller and smaller. Because then the number of circuits that you need to execute will be like out of the bound. It will be too large. And you can understand that wire cutting will also have similar effect. If you cut two wires, then it's basically the number of circuit executions is the product of each of them, the number of circuit executions required for each of them. So for most of the cases, you will see that circuit cutting has been limited to very toy problems like 5 qubit, 6 qubit. This, although I showed you 109 qubits, but this has a very particular pattern. Like I know exactly where to cut. I know that I need to cut the last and first qubit. So this is not really a random general circuit. This is a very particular type of circuit that was selected and shown that circuit cutting is useful. So the question is, let's put a number to it. I mean, many people keep asking that you say exponential, exponential. I understand exponential is bad. Exactly how bad? Can you give me an estimate? So let's take a number. This is a Hamiltonian simulation circuit, 1D Hamiltonian simulation. And if I cut this particular circuit, as you see, it requires 3 cuts, this, and this. So if you do 3 wire cuts, these are 3 wire cuts, and if you see gate cuts, you will need actually more. This. You will actually end up needing more cuts if you do gate cutting. So with the proper bookkeeping that we were discussing, it ends up saying that you need to run 1,536 circuits. So 1,536 circuit executions instead of 1. Now, this is very bad, right? So I hope you get a feeling why circuit cutting, using it very ubiquitously, is not immediately possible. So the question here is, can I reduce the number of cuts? That's not an obvious question, because say if you say that I am only going to use these 2 cuts, then you have not really partitioned the circuit into 2 sub-circuits, because you need to cut here. So the answer is not like that I'll not use these 3 cuts, I'll only use this 1 cut. Then you are not partitioning the circuit properly. However, the answer that we will see today is it is possible to reduce the number of cuts. First is by reducing the depth of the circuit itself. If I can say that, okay, my circuit is up to this much, then you don't need this cut. But then your question will be, but you were just showing it for this circuit. Now you have changed the circuit to say that I only have this much. That's cheating. That's not how you really do these kind of things. However, there is a technique called operator backpropagation, which can help you reduce the depth of the circuit. The second is selection of the cut location. Is this the best cut location selection, or can I do something better so that the number of cuts are reduced? This is the most obvious one. The one I am showing you here, this is the most obvious one. But can I do better? So can I have a better reason to select the cut locations? So these are the 2 words that I want to talk about. Let's first jump into this. To jump into this, let's quickly talk a bit about operator backpropagation, and it's super easy. Again, remember, we said that circuit cutting is feasible for problems where you want to calculate some expectation values and not if you want the final state of the circuit. So let's say, forget about circuit cutting for the time being for 2-3 minutes. So I have a quantum circuit and I have some observable O whose expectation value we want to calculate. I will logically partition the circuit. This is not physical circuit cutting. This is logically partition the circuit into, say, a quantum part and a classical part. What do I mean by classical part? So I will evolve this operator classical. So I'll take this operator, I'll put it here, I'll put it across the gates, and I'll see how the operator evolves. Then again, I'll put it across the gates and I'll see how the operator evolves. So if you keep doing that, this operator changes as some UC dagger OUC. So this operator gets updated. In the meantime, the depth of the circuit has reduced. So now, instead of saying that I need to run this entire circuit and calculate the expectation value of O, I can say I need to run this lower depth circuit and calculate the expectation value of O prime. These 2 are exactly the same thing. Why is this useful? Because this circuit is lower depth, so it will have lower noise. So let's take an example. Let's first take a Clifford circuit. So here is just an example circuit, and I want to calculate the expectation value of ZZ. So if I look into how do I calculate the expectation value, it's 0, 0. This is the gate operations. I want to calculate the expectation value of ZZ. So this is how we calculate the expectation value. The first thing that we do, we take ZZ and we cross it through C0. Now, ZZ crossing through C0, if this is not obvious to you, just go back and do this. It's a very simple calculation. When you take ZZ and put it before C0, it becomes IZ. So if I put it here, it becomes IZ. Now these two C0s are cancelled. They are the inverse of each other. So these two are cancelled out. Now again, I will take this I tensor Z and put it here. Now X and Z don't commute with each other. So we'll have a minus sign. So when you put it here, this becomes minus IZ. Once more, IX, they cancel out. So now, instead of saying that I want to calculate the expectation value of ZZ for this circuit, I can say that this is the trivial circuit, 0. I want to calculate the expectation value of minus IZ on the trivial circuit, which is 0, 0. So instead of doing this, I can do this. These two are same. Now, this is a Clifford circuit, so it was easy to backpropagate the entire circuit without any extra overhead. And this is the same as saying that Clifford circuits are easy to simulate. But not all circuits are Clifford, right? So in general, if you look into a circuit like this, there will be some Clifford gates, some non-Clifford gates, and I won't go into the mathematics of this too much. What it says is, whenever you have a non-Clifford gate, you can always write it like some exponentiation of some polys, right? Pi is some poly. It can be an n-qubit poly if this is an n-qubit gate, but it's an exponentiation of a poly. So what this Clifford perturbation theory, this is called the Clifford perturbation theory, what it shows is that when you have this observable O and this is a non-Clifford gate, two things can happen. This O is essentially a set of polys, right? It's a linear combination of polys. Any observable is. So it can either commute with P or anti-commute with P. If it commutes with P, you can actually backpropagate without any problem, the way we were backpropagating here, without any increase in the number of terms. But if O and P anti-commute, then the number of terms, then it kind of splits. Then you have two terms. So you have a cos theta with the original O part and a sine theta with P times O part. So you can understand one thing, or let's see an example first and then go there. So let's say that this is a general non-Clifford circuit, and I'm just partitioning just to make an example. There is no reason. Let's say that this is the quantum part, which I will actually execute on hardware. This is the classical part, which I want to backpropagate. So when I mean classical part, I want to backpropagate that part. Otherwise, it's a part of the quantum circuit. I just want to backpropagate. So once more, this is how we write it down. Once more, if I take ZZ and if I move past C0, it becomes IZ. The C0s cancel out. Now I have IZ. Now this and this, they don't commute. This is a non-Clifford gate. And first I will write it down like this. This is how we were writing it down. Exponentiation of some I theta. The theta will be X here. X and Z don't commute with each other. So we have a scenario of that Clifford perturbation theory that we talked about. P and O don't commute with each other. So X and Z don't commute with each other. So now I have a cos theta part with the original observable and a sine theta part with this new observable. Now, these two observables don't commute with each other. Like that's why the split. Since these two don't commute with each other, I need two quantum circuits to calculate. The first quantum circuit will calculate the IZ part. The second quantum circuit will calculate the IY part. And then we will just multiply with these coefficients and add. That will give us the expectation value. So in general, when you start backpropagating and you hit these non-Clifford gates, the number of terms in the observable, the number of non-commuting terms in the observable can double. And in the worst case, this can keep doubling in every layer and you can have an exponential increase. So that's why for any circuit, it's not easy or trivial to backpropagate it through the entire circuit, because then the number of terms that you need to keep track of, those that increases exponentially. It's kind of same as saying that in general, a quantum circuit is exponentially hard to simulate. But now, looking into this, we will make a very simple workflow. When you have a circuit, you decide on the maximum number of non-commuting groups. Here, the number of non-commuting groups is 2. If you say that I am willing to go for 4 non-commuting groups, I'll run 4 circuits. You can backpropagate more till you hit 4. So you can decide on the number of circuits that you can execute. That is called the maximum number of non-commuting groups. You backpropagate the circuit accordingly. Now my circuit becomes lower depth. So if my circuit becomes lower depth, potentially I can partition it with fewer number of cuts. So this is how we started, right? With the Hamiltonian simulation, we had 3 cuts. Can I do that with 2 cuts perhaps? Yes, if you can backpropagate up to that part. So it can be partitioned with fewer cuts when you backpropagate, but the number of circuits that you need to cut can now increase. Say here, if you say that I want to cut these circuits, I mean, these are single qubit gates, but anyway, let's assume that you want to cut these circuits. Now you need to cut 1 and 2. So now you need to cut 2 circuits instead of a
毫算
single
和量
qubit.
子计算的融合发展，已成为
So we cut the backpropagated circuit. So now we need to have a balance here. When I do more cuts, the number of circuit executions increase exponentially. When I backpropagate, in worst case, the number of circuits that I need to compute can increase exponentially, and then I have to cut each of those circuits. So I need a balance between these two. But first, let's take an example. This is once more the Hamiltonian simulation circuit. It's a smaller Hamiltonian simulation circuit. So this here requires 3 cuts, and the total number of circuit executions for this will be 576 because there are like 2 gate cuts and 1 wire cut. So the number of circuit executions is less. If I backpropagate up to say this part, right? So I remove the need to cut this gate, but the observable has updated. Now it has 2 non-commuting groups. So I need 2 circuits, 1 circuit for this part, 1 circuit for this part. So first is I have 2 of these. So I have 6 into 16. That's the total number of executions coming from circuit cutting. Now there are 2 circuits that I need to cut. So the total number of circuit executions is twice of this. However, you see from 576 to 192, there is still a 3x reduction. So the point is, if you do vanilla cutting, the number of executions increases exponentially. However, if you do backpropagation, there is a multiplicative increase but an exponential decrease. Now, as we discussed, when you do OBP and if you backpropagate too much, then the number of terms can keep splitting, and that this multiplicative increase can actually become exponential at that point. So the sweet spot is where the multiplicative increase is less than equal to exponential, ideally less than. Equal to means there is no savings, no gains. So ideally less than. So first, let me show you some results here. This is a 6 qubit efficient SU2 circuit, VQE circuit. So as you can see that if I cut the circuit, it requires 432 circuit executions. However, I can get the similar kind of result, in fact, slightly better. Why slightly better? Because the depth of the circuit has reduced actually. So the noise is slightly less when you backpropagate this circuit. So slightly better at a much less overhead. So 3x reduction. This becomes even drastic for 19 qubit Hamiltonian simulation. You can easily understand that this result is better where this was not so much evident. I mean, if you look carefully, you can understand this is slightly better. Here, you don't have to even look carefully. You can understand this is better. And there is a 10x reduction roughly in the number of circuit executions. And if we scale it up, we didn't run this circuit, but if you take, say, a 100 qubit Hamiltonian simulation, in vanilla circuit cutting, you have like 93,900 circuit executions. Whereas if you do backpropagation, it goes down to 1,000. So that's a 90x reduction. And if this doesn't like seem like a wow moment, let's look into this. If you want to run these many circuits, and this is kind of the execution overhead, this would require 6.2 minutes. whereas this would require 4 seconds. Now the question that, so it kind of shows the beauty of this method, like, right? Now the question that you can ask here, if you have been watching carefully, you can ask that you took max QWC 4 here, you took 18 here, how did you find 4 and 18? Why not anything else? So let's answer this question first. So first what we tried to do is, as we increase the max QWC, we tried to calculate the number of sub-experiments, means the number of circuit executions. And we tried to see if there were any patterns. Apparently there were not. So this is for VQE, this is for Hamiltonian simulation, and there are no patterns that we can exploit. So something like gradient descent will not work here. So what we did, there can be other methods to do this also. We did simulated annealing. So if there are anyone who doesn't know simulated annealing, it's kind of like gradient descent. It says that when you are sitting here, you choose a next point. If the energy of the next point is lower, then you definitely go. If the energy is higher, you go with some probability. So, and this some probability depends on a parameter called the temperature. Initially, you start with a very high temperature and slowly you settle down. So that means initially you have a higher probability of selecting a bad next move. But as you go with the process, the probability that you select a bad move is actually reduced. So this is a heuristic process, but the reason it often works better is that it helps you to avoid these local optima, because you are sometimes actually going uphill or something like that, selecting bad results as well. So here we did this kind of a simulated annealing. Remember, it's just a classical experiment. There is no quantum overhead here. And this simulated annealing gives us the best max QWC. So if I want to summarize this very quickly, you see there are Qiskit add-ons for both of these, OBP and circuit cutting. We tried this for all circuits in the bench press dataset as well. So bench press is a dataset that has different kind of circuits of different size going up to 64 qubits. So we actually showed these results for up to 64 qubits, and circuit cutting with OBP in all the cases reduces the number of circuit executions. Now, let's say there are some edge cases we didn't find in all these experiments, but there are some circuit where this circuit cutting with OBP doesn't help. But if it doesn't help, then it actually reduces to vanilla cutting. So OBP plus cutting can never give you a worse result than vanilla cutting. The verdict here is a very strong verdict, but it is as it is. Circuit cutting should always be associated with OBP as the pre-processing step. All the results show improvement, and we show here actually analytically as well. This is just written here in the paper. We discussed this analytically, that if there is no improvement, it is as good as the normal circuit cutting. It can never be worse. So there cannot be any scenario where you should be doing circuit cutting but not doing OBP. Let's quickly cut to the second part of this. I'll go quickly. So this was kind of saying that I can reduce the depth of the circuit and hence reduce the number of cuts required. The question here is the location of cut. Can I select the location of cut more intelligently? The question is, how do we select it today? You can select it manually. The best method that we have today from the circuit knitting toolbox, it's called an automatic cut finder. It's basically a heuristic tree traversal based algorithm where you input the device constraint. Now, this device constraint is how many qubits are allowed in each subcircuit. If you give that, it will do a heuristic tree traversal with some pruning and all alpha beta pruning kind of things. Those of you who are from computer science will know these alpha beta pruning things. And it returns those cuts. It can be both wire and gate cutting together. That leads to the minimum sampling overhead. That means the minimum number of circuit executions. Now the question then becomes, how do you select a good device constraint? You can ask that, is that a really important question? How do you select a good device constraint, or you are just trying to come up with research questions just because you have to? So let's take a 6-qubit 1D Ising model here. Okay. And if I don't give you any information on how many qubits can be in each subcircuit, if I don't tell you anything, what is the natural thing you will say? Let's do a 50-50 cut. So let's say that out of 6, 3 will be in subcircuit 1, the rest 3 will be in subcircuit 2. So if you do that, it leads to around 6,000 circuit executions. However, if you make your device constraint 4, if you allow 4 qubits in one subcircuit and 2 qubit in the other, it becomes 1,200. And if you just reduce it by 1, if you make your device constraint 2, the number of executions increases by 6,600 times. So this question, how do you select a good device constraint? It's an important question. It's not a question that we are framing just for the sake of it, right? So beyond naive selection, like 3 device constraint is the naive selection, but doing 4 is better. How do you know that for a circuit? If I give you a circuit, how do you know that going from 3 to 4 is actually better instead of just like randomly trying everything? So here we come up with a noise-induced cut location selection. The idea here is that a quantum circuit, if you look into the IBM quantum devices today, all the qubits are not equally good or equally bad. Some of the qubits, some of the connectivities, they are more noisy, some of them are less noisy. So the question that we asked is, can I use this information to find my cut location? How do we do that? First, we puncture the hardware coupling. So let's say this is my hardware, and say these are the qubits or the 2 qubit connectivities, which are way more noisy than the rest of the qubits. So we first identify these way more noisy qubits or connectivities, and then we remove those. So this is what we call as punctured coupling map. So these gray parts are the removed parts and the blue parts are the retained parts. So when you create this punctured coupling map, most likely the coupling map becomes disconnected. So these blue parts, these are some connected components, and the size of these tells you the maximum size of circuit that you can run on this part. And this is what we call as low noise islands. So we just termed these as low noise islands because these are more noisy. That's why we removed them. So these are some islands of low noise. And I want to create my subcircuits in such a way that they fit in this part. Because that means not only my subcircuits are smaller, but also my subcircuits can run on the good part or the better part of the hardware. So this was the reason of going through like this. This gives you a device constraint, which is not naively selected, which is motivated from the hardware noise information. So S max is, of course, for this example, it is 9. S mean from this example is 1, but see, taking 1 doesn't make a lot of sense. So if you have a circuit with, say, 10 qubits, what we selected is my S mean will be just divided by 2. So that's equal partitioning versus going up to the largest circuit that we can accommodate in any of these good layouts. So that's my device constraint. It's everything between S mean and S max. So what we do here, we take the cut budget from the user. The user needs to take the cut budget because that's the number of circuits the user can afford to run on the quantum system. So we, for each S, that's the device constraint, between the range, sorry, this should be S mean to S max. So in the range S mean to S max, we take each of the S, we put it as a device constraint to the automatic cut finder. The automatic cut finder will find the subcircuit, the cut locations. Now we select each of those things and we do a post-processing on this. I'll tell you what the post-processing and why we need the post-processing. Just the thing to motivate here, you see all of these values between S mean to S max, these are independent computations. So you can actually put it on an HPC and you can parallelize all of these. There can be multiple values. If you parallelize all of these, this becomes much faster. So you can do this in what we call as the quantum-centric supercomputing kind of way. Now, here is a problem. So the cut finder, what it does, the automatic cut finder, it will return to you a cut strategy with the lowest sampling overhead, the lowest number of cuts. So say if you end up giving a 10 qubit circuit, it can find, and if you have your S max as 9, just like we had S max here, it can give you a 9:1 cut. One sub-circuit has 9 qubits, the other has 1 qubit. So this is not a good partitioning, because then most of the gates and everything are going to that 9 qubit partition. The 9 qubit partition will be almost as noisy as the original circuit. So all our requirement that you kind of want to reduce the noise in the systems, that is lost. So this is one problem that can happen from here. The other problem is, so let's say that I have my 10 qubit circuit, which I can map very efficiently on this hardware coupling map, on the original coupling map. But when I remove some of the qubits and edges, it's possible that the mapping is no longer so good, and the subcircuits require way more swap gates just to do the mapping in this part of the hardware, because I am removing some part of the hardware from your availability. So we need to take care of these two things. And the way we do this is slightly indirect. We need a method to discourage highly unbalanced partitioning. But that doesn't mean that I want 50-50 partition, because I showed you that there are better partitions than 50-50. Just a slight increase is actually better. So we also want to discourage partitioning, which will lead to many swap gates for placement. So we do this, as I said, indirectly by doing this weighted average cost function. So this is the cost function that we are trying to minimize. S is the total number of sub-circuits. This is a weighted average. So alpha and 1 minus alpha are the weights. The first part, this part, which is the norm 1, it is the average layout score. This S is the layout score for sub-circuit I, and N is the number of qubits in sub-circuit I. So this is the weighted average, and Ni is the number of qubits in subcircuit I, N is the total number of qubits in the entire circuit. So this ensures that the average layout score is low. Indirectly, it means if you end up having a cutting strategy which leads to many swap gates required for the subcircuits, the total layout score, which is a function of the noise in the hardware and the size of the circuit. So you are already selecting low noise layouts by doing this puncturing. So the primary thing that this layout score is capturing is the complexity of the circuit. So the fact that we are trying to minimize this makes sure that you don't end up having a cut strategy that requires too many swap gates for placement. At least more swap gates, too many more swap gates than the original circuit. So this ensures a good layout selection and low swap strategies. And this is kind of saying that you reduce the variance as well. So it avoids scenario where, say, you are doing a 9:1 cut. The mean can become very low because 1 will have almost zero noise, whereas 9 will have the majority of the noise. So if you take the mean, it will seem as if the noise has reduced. That's not giving you the full story. So we are taking the variance part here. If you see, this is the mean part and this is the variance part. This is kind of saying that you want to have the subcircuits more or less balanced. Don't go for too unbalanced ones. Something that we tested over multiple things is that these two are highly correlated. So you can actually remove this part and just keep this one. The alpha will not be here, sorry. So if you just keep this one, there is no weightage. So it's just this part. So let's show you the experimental results. This is a 20 qubit mirrored QAOA circuit. The reason for mirroring is because we know the final outcome. So here, if you see, if you do an equal partitioning, it requires 2,590 circuit executions. By selecting the cut location with this, what we call as this hardware inspired cutting, you can get it down to 128 and you can retain a similar performance. This is the weighted average. So you see the weighted average actually decreases slightly here. In this case, if you do the hardware inspired cutting, that is not always true. here, if you took we took a 20 qubit random circuit, because you can feel like, okay, this is a very structured circuit. It works for structured circuit. Does it work for any circuit? So here we took a 20 qubit random circuit, but a Clifford circuit because we needed the ideal outcome. So here also you see the weighted average increases slightly here. See, that's expected. The weighted average will be lowest for equal partitioning, but we don't want to always go for equal partitioning. So here it increases slightly from 0.38 to 0.4, but that doesn't really do a lot of difference in the execution here, the quality of result. It's still the same, but the number of circuit executions reduces from 5,000 to less than 100. So this is a huge savings that we get even on a random circuit without any loss in the quality. Now, this can give you a false hope that by doing hardware-inspired cutting, I can arbitrarily reduce the number of cuts. But this doesn't sound right? This doesn't sound correct. I cannot arbitrarily reduce just by doing this kind of thing. So here is an example where if you do the cut budget to 2, going from equal partitioning, it reduces significantly. So this is just so it goes to 192 circuit executions. The weighted average doesn't increase a lot and the quality doesn't change. But if you even try to further reduce it down to 18, it actually lowers. The quality actually gets lowered, and that is actually indicated by this weighted average. So what we are trying to show here is two things. First, you cannot arbitrarily reduce the number of circuit executions of circuit cutting by this method, but you can still do a lot of improvement. And this weighted average, the cost function, is actually a valid indicator of the quality of circuit. How good is it? How bad is it? And so on. So here the increase is slight. It's negligible increase. Here it's not negligible increase. And you see the quality is same here. The quality is not same. So using this, we went to a 50 qubit QAOA circuit. Here you can see that if I do an equal partitioning, it requires something like 43 lakh circuit executions or something. Whereas I can use this hardware inspired cutting trick and I can bring it down to 256. But here we expect that the result, the quality of result is going down somewhat because of this hardware inspired method, because there is a non-negligible increase in the weighted average. But here is a point. You couldn't even use circuit cutting if you don't play this kind of trick here, because this is like an absurd number of circuit executions. So you can't even do circuit execution on a circuit of this size. But today you can, using this hardware inspired cutting. We understand that this is going to reduce the quality, but we don't know how much the quality reduction is because we can't even run this circuit. So circuit cutting becomes possible for circuits which was previously not doable. And we tested this for this bench press circuits, the one I talked about before also. And we showed that if you take average score for equal partitioning versus hardware inspired cutting, you see very negligible change in many of these circuits. And the reduction in the number of circuit executions is unbelievably good. I mean, 99% reduction, 93% reduction. So what it shows is that this hardware inspired cutting consistently reduces the number of circuit executions, but with a caveat that we shouldn't feel like that we can just use this trick to reduce the number of circuit cuts required arbitrarily. That's what we showed here, that if you try to be too smart, you lose in quality. But at the same time, you can actually do circuit cutting on circuits which were previously not possible. So I'll end with this summary that, as I started by saying, that think of circuit cutting as an error mitigation technique, not as a technique to run larger circuits on smaller devices. It kind of gives you what we did today with hardware inspired cutting technique, the last one. It shows you an avenue that you can use circuit cutting for much bigger circuits which were not previously possible. And you can actually, in the same process, you can select good layouts for them. So you don't really need to randomly select cut locations. You can use the hardware non-noise information to tell you what is the optimal cut location. What we didn't do here is putting this operator backpropagation together with hardware inspired cutting. Nothing is stopping us from doing that. If you put both of these together, it will give you an even more improved result. The reason we didn't do that is for both of these, we wanted to show the improvements that each of these methods bring to the table. None of these results are with error mitigation. So note that you can improve the results here further with error mitigation. The reason we didn't do error mitigation in both of these experiments is to like avoid people coming and saying that, oh, it was not your method that is doing the improvement, it's error mitigation that's doing the improvement. So you can actually further improve these results by putting operator backpropagation, by putting error mitigation. So I'll stop here with this, that this is what we did, and it brings circuit cutting closer to doable on much larger circuits. But there are still many works to do. So thank you for listening to this.